Alright, so what's up? I'm the Nature Hacker. This is your world. And really quick, I just wanted to say why I do what I do. I'm here to bring the knowledge back. Basically, I'm here to empower a grassroots movement to basically to take the knowledge back, to take the power back. Basically, if I want to make it so that monopolies don't happen, I have to empower the grassroots. Okay, so that's what I'm here to do. I'm here to empower you so that you can be the innovators, the leaders, and that you can obsolete the monopolies. That's why I'm here. That's why I'm doing what I'm doing. Alright, so I'm trying a little bit of a different thing on the stream. So, you know, hopefully it's a little better quality on the stream, so we'll see how this works. Anyway, today what I want to talk about is light, and how light is a gas, and the smoking gun of that is how a radiometer works, a Crookes radiometer. So, this has to do with NatureHacker's fourth law, which is that there has to be a force transfer in order for you to get movement. You know how they say, oh, you know, for every action there's an equal and opposite reaction, but in order to have a reaction, you have to transfer that action from one thing to another. If you're not transferring that force, then you're not going to get any reaction. So you have to transfer the force, and that's the whole basis of my rockets don't work in space argument, is that without friction in space, the air molecules can't transfer. The air molecules you're shooting out of the rocket, they're not transferring their force to anything, so they can't create a reactionary force. So that's NatureHacker's fourth law. You can also Google NatureHacker's fourth law and see, you know, things I've written on it and stuff. So it's force transfer. There has to be a force transfer. So one interesting thing about the radiometer is, let's be honest, you know, if you look at the thing, it's that thing with the white squares and the black squares. One side of the square is white, one side is black, and you know, they spin around in this little light bulb looking thing. So if you look up, if you want to pause this video right here, or you know, pause the stream, I don't know how a stream works, I think you can pause it. Look up what a radiometer is. So anyway, let me describe to you how it works. So this is what they say. Okay, this is not exactly how it works, but this is, I'm going to first start with what they say. They say that the light comes in, it's absorbed on the black side, the black side heats up, and then that creates extra air pressure, which pushes it forward. Okay, first of all, this is dumb. Okay, when you look at a radiometer, you know just intuitively that it's working because of light. Light is transferring its kinetic energy into the system and propelling that thing around, right? It's just the light that's doing it. It's not light converted into heat and da-ba-da. No, you know, if you cooled the thing, it'd work even better, okay? If you evacuate the air from it, you're getting rid of the air from inside of it. It works better. The better vacuum you have, the better it works. That means the air is not needed. The air is not needed. It's not air pressure that's turning. It's actually the radiant energy of radiation. That's how it works. And you're like, oh, it also works with a hairdryer. Yeah, doy, a hairdryer is actually radiating as well. So it's radiating. Radiant energy is called infrared. It's still radiation. Okay, so a Crookes radiometer, guess what, works on radiation. Okay, I think Crook knew that probably because he called it the radiometer. So obviously he's working on radiation. It's not working on heat or air or any of that BS. Okay, so anyway. Now, why, if it's working on radiation, you would think that the side that's white would get the side that gets pushed most by the light, right? Because like say you have a billiard ball, if you have two billiard balls, and one of them goes and sticks, okay, you get less speed than if this one goes and bounces off. You get more speed because not only is this one sustaining the hit, all of the force from this hit but also all of the force from it being bounced back. So you get all of this force and then all of the force required to make it bounce back. So you're getting like double the force if it bounces back. But if it sticks, you don't have as much force. Okay, so you would think that the white side would be better because the white side is reflecting the light, right? So if you're not only taking all that momentum from the light, but also giving it more momentum in the opposite direction, you would think it'd be pushed double as strongly, as fast as you know, if it were just sticking. But here's the key, here's the kicker. Here is the smoking gun, here is the explanation that based on our knowledge of NatureHacker's fourth law. Alright, and you know, I call it NatureHacker's fourth law just because Newton called it the first or third law or whatever. But really, this is your law. The reason I'm doing this, I'm giving you this so that you can use this knowledge to create innovation. I want to bring the knowledge back so that we are more powerful, because knowledge is power, so we have more power than the corporations. That's what I'm doing. I'm creating the grassroots. All individuals, empower all individuals. They can't take it out. If you have one corporation, it can easily be taken out. But if you have the grassroots, that is unstoppable. So that's what I'm here doing. So now this is a key right here, because remember, it's the same with gas, right? Let's say you have a plate here and you have a vacuum all around, like we're in space, right? And you're shooting gas at this plate. Is the gas going to, you know, bounce off? Is it going to go around? Sure, yeah, it's going to. But the key is that it's not the light. Or sorry, the gas is not confined. It doesn't have to bounce straight back. It doesn't have to bounce back at this angle. It can bounce. It can take the path of least resistance. So there's no force transfer. If you have a plate in a vacuum and you're shooting gas at it, there's no force transfer because the gas particles are not constrained. NatureHacker's fourth law says the gas particle, or basically you have to constrain the motion. The motion has to be fully constrained in order to do work, in order to create a change in motion. Okay, you have to have fully constrained. So if you have a straw leading that gas molecule all the way to the plate, and then you have like a little divot in the plate where it has to push on it, then it will. But if you pull that straw out, the gas, instead of pushing the plate away, it's just gonna zoom off in another direction because it's not forced to do anything. Okay. Now here's how this applies to the radiometer, because light is a gas, and I've already said this in a video or two that light is a gas. So what that means is that light is it gonna reflect? Sure. Is it gonna, you know, if you have light coming here, is it gonna reflect out here? Yeah, absolutely. But it's not going to transfer any momentum. It's not, because it's not constrained. You're not constraining that light. You're not saying, hey, light, you have to bounce here and then go back here. If you're constraining it, then yes, it will transfer momentum. But if you're not constraining it, it'll just go wherever it wants without having to transfer any force. Because things don't want to have to transfer force. Transferring force is doing work. And things do not do work unless they are forced to in nature, okay? So, you know, everything in nature takes the path of least resistance, you know. So, anyway, in order to get light to do work, guess what you have to do? You have to constrain its motion. You have to tell light, no, you can't go. You want to go this way? Or you want to reflect that way? No, you can't do that. You have to, you know, either reflect this way. But in general, reflection of light isn't transferring momentum. It's the opposite of the billiard ball, okay? It's the gas effect, because light is a gas, so it behaves like a gas. And a gas will not transfer momentum unless it is forced to, unless it is fully constrained. Like a barrel of a gun, you know, that gas, to expand, it has to push the bullet, so it will. But if you have a hole in the barrel, the gas doesn't have to push a bullet, it can just go through the hole. Okay, so that's the same thing here. Light, unless it's forced, will not transfer momentum. It will just take the path of least resistance. It will escape. Okay, light reflecting in general is escaping. All right. Now, so, you know, you're like, well, what if we do a mirror or something? You know, you're forcing the light to go a certain direction. Are you going to get momentum transfer? Maybe, but I'm not exactly sure. But what I do know is that if you absorb the light, you are constraining its motion, absolutely. You are taking all of that energy of the light, all the kinetic energy of the light, and you are stopping it. You are absorbing it. So you're taking that energy of the light, absorbing it. So you're getting momentum, transfer of momentum from the light to your thing. Okay, so that is how the radiograph works. Is it the black side absorbs the light and allowing you to capture the kinetic energy of the light. Absorbing the light allows you to capture the kinetic energy of the light. That's how plants work. The chlorophyll absorbs the light and it gains the energy of the light in order to, you know, make carbohydrates or whatever it does with the light. You know, also, let's say you have a black piece of paper out there, it gets hot, you know, or you have a black car, it gets hot, right? What's happening is you are absorbing the light and you are getting the energy, the kinetic energy of the light is being converted into heat. Okay, so that's what's happening. You have to absorb the light in order to gain energy from it. So that's how the radiometer works, is the black side is absorbing the light, and that's why it goes, here's a black side right here. You absorb the light, and that's why it pushes it. It pushes it that direction when it's spinning around. So, you know, this obviously has implications for space travel. You know, I've talked before, it's like, okay, well, if rockets don't work in space, what does work? And I thought light did. I thought, like, because, you know, a light beam, it doesn't go out in all directions like a gas would. A light beam goes forward, right? And it slowly expands as it goes back. So I was thinking, well, you know, since it's constrained, right? It's constrained in its direction. It's not going boom all directions. It's constrained, so you will get some momentum when just pushing the light out of your craft. You will get momentum, but that's wrong. And the reason it's wrong is because light actually is expanding out in all directions, but it's just moving so fast that it takes a while to see that process happening, okay? But it really is expanding as fast as it wants to expand. You know, it's not being constrained at all. So you will get no reactionary force if you're just shining light into a void, all right? So light will not work. Light will not work to propel a spacecraft. You know, the way it would work is if something's absorbing that light, something is constraining the movement of light, something is absorbing it, okay? So if that's happening, if something's absorbing the light, then you can use light to push yourself off of something, okay? The problem is that there's not much out in space that absorbs light, okay? You know, you could shoot the beam at Earth and Earth will absorb the light. You know, if you shoot it into the ocean will absorb that light, you know, and you'll be able to propel yourself with light off of the ocean, or even a forest. You know, forest absorbs a lot of light, like especially if you're using a green laser, right? If you're using a green laser, yeah, a green laser and shooting that at the forest, then that forest is going to absorb a lot of that light, you know, if not all of it, you know, so you can push off of the forest. But, you know, if you're that close to Earth, you might as well just use a rocket, because you have air pressure to push off against with the rocket exhaust. You know, if you don't believe this stuff I'm talking about, I've done a long thing on how rockets work in space and stuff, so you can go back to those videos and check out what I believe about that. And I feel like I've offered a lot of proof, a lot of evidence to that theory. So, now what we have is we have light, and we know what light is. It's a gas. And you know, you look in space, you're like, you know, well, maybe space is absorbing it. Maybe space would absorb it. I mean, eventually it would, but really you have to be transferring that force to something, you know, and that thing could be far away in light's case because it moves so fast, you know. So maybe you could be pushing off the Earth for a pretty long distance, or pushing off of the asteroid belt or something that's absorbing the light. And that could be a possibility. That definitely could be. You could definitely help steer yourself with that. But where I'm going with this is let's come up with a method for space travel. And I think that who's that Nazi? Is it Goddard, or is it one of these Nazis came up with this plan of a space station because they know that rockets can get pretty much into orbit. They can get up to pretty high, but you can't really go beyond that, and they knew that, and that's why they said, okay, we'll make a space station. That's the whole reason we have space stations. I don't even know if they're really functional at this point or what, but the whole premise behind making a space station is that rockets can only get us so high. So how about we get them up to a space station, then we go from the space station up higher. The problem is rockets don't work higher, so that wouldn't work with the technology of the day. But let's say we can get up, so we use rockets to get to a space station, right? And then how do we get from that space station higher? My thought is spray foam. Okay, literally spray foam can get us higher. You have something on the bottom of something where it's maybe like has jets, and you have a rotary thing where it's rotary jetting spray foam up. And spray foam is good because what it's doing is it's containing the gas. You can use hot gases, but they're contained in bubbles, right? They're contained in bubbles of like polymer or whatever you're using. You could use a cellulose polymer. That would be great because it's biodegradable, right? So you're creating these bubbles, and as these bubbles expand, they're transferring momentum. They're moving you higher. As the bubbles expand, they're moving you higher. So you're creating this thing of spray foam that's expanding and shooting you up. So it's like you'd be riding a black snake. If you've seen black snakes in fireworks, it's like you'd be riding a black snake up to the moon or something, So anyway, that's how we get around maybe we get to the moon, is we ride up a black snake of bubble polymer spray foam up to the moon. Okay, I know it sounds crazy, but really that's how you would do it. Now, once we're on the moon, we're farther away from Earth's gravitational pull. Gravitational pull, it's really an electrostatic. Gravity is just electrostatic attraction. It's just a very basic induced electrostatic attraction. So if we get a little farther away from the Earth, let's say we're getting to the moon, that'd be a great launching point to get farther. And now what we're going to be doing is we're going to want to catch a wave. Ultimately, what we would want to do is catch the solar wind. We would want to sail on the solar wind. Now, a lot of things like that NASA's proposing and stuff for sailing on the solar wind have been reflective, right? Reflective sail materials, because they're thinking, okay, if you're reflecting the light, boom, you're getting the maximum amount of momentum transfer. Well, we know that's not true because light's a gas, so it's just going to go, it follows straight lines, sure, but it's following the path of least resistance. It's just going in the path of least resistance. So unless we're capturing that light, we have to capture that light in order to get the energy out of it, unless to transfer the momentum of the light into our sail. So guess what color our sail has to be? Black. And not just colored black. You want it to be really absorptive. Like what I've done we had to do a solar oven in school, in Engineering 101, and everybody did, they paint the bottom of their solar oven black, right, so that it's absorbing the light, right? Oh yeah, good, great. No, but I knew something a little deeper than that, and that, black is still reflecting a lot of light. There's probably 20-30% of the light being reflected off of the black surface. So how do you capture more of that light? What I did is I sprayed some adhesive. I painted it black, right? Matte black, obviously, because shiny black will reflect a lot of light. So I painted it matte black. Then I put some spray adhesive in there, and I took crushed up, basically powderized construction paper and sprinkled it in there. So powderized construction paper sprinkled in there, okay, and then I put some spray on that and did some like crunchy pieces of chopped up construction paper, thin, crunchy pieces of construction paper, because what you want that light to penetrate deep into all this jumbled junk, and if it ever does reflect in there, it reflects and hits another piece of junk. Hits the other piece of powdered construction paper, it hits the piece of jumbled construction paper. You don't want it to ever leave. Every reflection, we're going to have reflections, but every reflection needs to be further absorbed by that jungle material there. So that's what we would want. To get a solar sail, we would want very, very black. But not only that, because the sun isn't only putting out infrared and visible and ultraviolet radiation, which you can capture with construction paper and stuff, but it's also putting out a lot of charged particles. And you're really going to want to try to ride those charged particles. So how are you going to constrain the motion of charged particles? Again, obviously you're going to want to attract them. You're going to want to absorb them. And how do you absorb charged particles? You have the opposite charge. So let's say you have a bunch of negative charge on your little sail. You have a bunch of negative charge here, so when the positive protons are coming from the sun, you're absorbing those protons. You know, if you had positively charged here, you know, and you had positively charged protons coming from the protons from the sun would just zoom, go around you, okay? But if you're negative, the positive charges are going to stick and they're going to transfer their momentum to you. You don't want to reflect things. When you're talking about gases, when you're talking about light, which light is a gas, it's just a special case of a gas, you don't want to reflect things, you want to absorb them in order to get the momentum to transfer. So we could have sails, that's how we could go mine these planets and stuff. We get to the moon with spray foam, you know, rockets up to orbit, orbit to the moon, spray foam, moon to the other planets, we'll use sails, riding the solar wind by absorbing the solar wind, okay? And then beyond that, I don't really know. I don't really know how to move beyond the solar system, but I think that's good enough to get us started, right? I mean, you know, let's not be dumb and try to, you know, go to Andromeda or something right off the bat. First, we need to mine the solar system. We need to mine the moon. There's a lot of silica up there. You know, we could use the moon to be harvesting solar energy and beaming the energy back to Earth in the form of like lasers or whatnot. So anyway, that is how to get us started in space travel, and all of that is because we know how gases and how light actually behaves, and we know NatureHacker's 4th law and 5th law too, so you might want to look those up to get more information. So I'm here, like I said, the why of why I'm here is to empower you. I know that the only way that we can get rid of the monopolies in our society that are absolutely farming us. You know, these monopolies have taken the form of empires in the past, but today the monopolies are in the form of giant corporations that monopolize and create the laws. They lobby to create the laws. So anyway, thanks for watching. I'm the Nature Hacker. Go do work.